One of the key figures in the quantum revolution is a young Dane with a tendency to mumble. He's the scientist on the right. His name is Niels Bohr. And from childhood, it's physics that consumes him. Once, while playing goalie in an important soccer game, he starts scribbling equations on a goalpost. Only the screams of an ardent fan snap him out of his reverie in time to stop an opposing player's potential goal. At school, he's an excellent student, though he seems to have a serious phobia about writing. As a graduate student, he dictates his entire doctoral dissertation to his mother, causing a family fight when his father insists that the budding PhD learn to write for himself. He never does. After his marriage, his wife gets the job. In 1912, shortly after receiving his doctorate, Bohr travels to England. He comes to Ernest Rutherford's laboratory just 1 year after Rutherford makes a startling discovery about atoms. Atoms had been seen as amorphous blobs of positive charge studded throughout with negative electrons. In fact, Rutherford says, they're more like little planetary systems. All the positive charge and virtually all the mass is concentrated in a tiny nucleus, around which the electrons orbit like planets around the sun. This is the courtyard at Cambridge University, where Rutherford began and ended his scientific career. Imagine an atom this size.
If we think of that being the size of an atom, then the size of the nucleus would only be 1 millimeter in diameter. That's a bit smaller than this little grain of sand that I've got in my hand here. In other words, what it means is atoms are essentially empty space.
Now, how can we reconcile that with the fact that matter is matter, and my hands don't go through one another? Well, that's crazy, because if it's mostly empty space, they should pass right through one another. Well, what we understand now is, in fact, that the reason my hands don't go through one another is that while the space is empty, what it's filled with is really electric fields.
When the electrons come within a very small distance of each other, they begin to repel each other. So we have the illusion that things are solid, when actually we have this tremendous vacuum given by the fact that the atom is basically empty. Now, this means that I'm not really sitting in this chair at all. The atoms of my body are about 1 angstrom hovering over the atoms of this chair.
Rutherford's conception of the atom is a breakthrough, but almost immediately he finds a paradox at the heart of it.
See, the problem was that if you've got a nucleus with a positive charge and electrons in orbit about it, then we know that the electron should very rapidly orbit into the nucleus. It should do it in a fraction of a second. That's a very secure prediction of classical physics. And that's catastrophic. What it's telling you is that atoms cannot exist. It means that you and I would not exist. The atoms would have no way of supporting themselves with the large volumes that they have.
When Niels Bohr arrives in Manchester, Rutherford is ready to abandon his model of the atom. But Bohr sees a way to save it.
He was so excited, he canceled his honeymoon. He had to delay his wedding, cancel the honeymoon, and his poor fiancée, instead of going on a luxurious honeymoon, had to take dictation as her husband dictated one of the greatest masterpieces in physics because he himself could not get himself to write down the paper.
What he proposed was that you would not allow the electrons to move in any orbit about the nucleus, as you could according to classical theory, but only to occupy certain very well-defined orbits about the nucleus. There would be an orbit here, an orbit here, an orbit here, but there would not exist orbits between these.
There's nothing in between. In between exists nothing. And that's very non-Newtonian. If you take the Earth and you could move the Earth a little bit closer to the Sun, no problem. It would have a different orbit, would be stable, would have a different time to go around the Sun, no problem. That you cannot do with an electron around a nucleus. You cannot just change the orbit by a little bit. You have to change it by, so to speak, a lot.
Bohr's idea that electrons can have only certain orbits draws inspiration from other new theories that suggest heat and light come in units that can't be divided, called quanta. But applying this quantum idea to matter is practically sacrilegious. In fact, most physicists disapprove of Bohr's theory. Whenever they meet, they scoff at the idea that an electron can be in some places but not others, that matter comes in some sizes but not others.
If it's not nonsense, at least it doesn't make sense.
This is just a cheap excuse for not knowing what's going on.
The assumptions are too bold, too fantastic. They can't be right.
In time, two camps emerge. A group around Bohr, which believes in his so-called quantum theory of matter, and those who cling to the classical view. No less than the true picture of nature is at stake. In 1926, Werner Heisenberg, a 25-year-old German physicist, comes up with a mathematical description of atoms that goes a long way toward legitimizing Bohr's view. Classical physicists remain unconvinced. Heisenberg's mathematical matrices are too complex, and the mysterious comings and goings of electrons are just too hard to imagine. Within a year, an Austrian named Erwin Schrodinger offers an alternative.
Schrodinger had this beautiful theory of the electron as a wave. It was smeared out over space and time. It wasn't a particle at all. Physicists loved this idea. We had a physical picture. We could look inside the atom. Physicists knew how to calculate with waves. They calculated waves as an undergraduate in college. They knew how waves went around and formed orbits. So the appeal of the Schrodinger picture was that it was pictorial. It was almost Newtonian. It was continuous. None of this quantum business. And you could calculate with it.
So which is it? Is matter made up of waves or particles? They seem to be complete opposites. Waves can pass through one another, sometimes canceling each other, sometimes making even bigger waves. But particles, on the other hand, bounce, smash, exert force when they meet. They can't cancel each other out.
So these two pictures clashed with each other, and they debated. And they had arguments, and they yelled and screamed at each other. In fact, one day, Heisenberg was so worried that he simply came down with hives and hay fever and tremendous case of allergies, worrying about whether or not the rival picture was correct.
In 1926, Bohr and Heisenberg invite Schrodinger to Bohr's new institute in Copenhagen to try and work out their differences. Heisenberg writes about the visit.
Though Bohr was an unusually considerate and obliging person, he was able in such a discussion to insist fanatically and with almost terrifying relentlessness on complete clarity in all arguments. He would not give up, even after hours of struggling, until Schrödinger had admitted that his interpretation was insufficient. Every attempt from Schrödinger's side to get around this bitter result was slowly refuted, point by point, in infinitely laborious discussions.
Bohr's wife nurses Schrödinger when he falls ill from exhaustion. She brings him tea and cake, even as her husband sits on the edge of the bed continuing the argument. Still, Schrödinger clings to his classical view, wearily noting at one point, if one has to go on with these damn quantum jumps, then I'm sorry I ever started to work on atomic theory.
The essence of the Bohr-Heisenberg picture was that the electron was a particle. However, there was a certain amount of uncertainty with regards to where the particle was. Now, one day, Heisenberg was so paralyzed, worrying about all these problems, that he took a walk in the park. Outside his institute, there's a famous park, and late at night, he walked through the park wondering, how can it be? How can it be that you don't quite know where the electron is? And then in a flash, he understood. Because to understand where an electron is, you have to look at it. To look at it, you have to shine a light on it. But when you shine a light on it, that disturbs where the electron is. So the very fact of observing an object changes its location. Therefore, he realized that uncertainty is an essential part of his picture.
Heisenberg calls his insight the uncertainty principle. In a clear mathematical way, it says the more you know about a particle's position, the less you can know about its speed and direction. And the opposite is also true. The more you know about a particle's speed and direction, the less you can know about where it is at any given time.
And when he finally had that idea, he realized that he could merge the Schrodinger picture with the Bohr-Heisenberg picture to give us the modern-day theory of the quantum principle. In other words, the electron is a point particle, but you don't know quite where it is. And the probability of finding it at any given point is given by a wave, the Schrodinger wave. So we now have this beautiful synthesis of waves and particles.
Heisenberg's principle, indeed, is very, very non-intuitive. Frankly speaking, I'd call it bizarre. But you can see it at work. Suppose I have a laser beam here. And I use laser beam because that's right, but I could use any other light for that matter. And I make here an opening, a slit, a vertical slit. And here goes the laser beam right through the slit. Light goes on, and here I project this onto this wall or screen, projection screen, and what do I see? Well, you see exactly what you predict. You see here this laser spot from this beam. But now I'm going to make this vertical slit narrower and narrower and narrower. What now are you going to see? Well, you're going to see exactly what you predict. You're going to cut off the edges of the circle, and the spot gets narrower and narrower and narrower. But now you come to the point that this narrow slit, say, is only 1/100th of an inch wide. And now Heisenberg's principle comes in. Because now you know so precisely in the horizontal direction where the light is, that as it emerges from this slit, the direction of the light is no longer determined according to Heisenberg's principle. And so now what you're going to see, it's going to spread out in the horizontal plane, and therefore what you're going to see on this projection screen is going to get wider. Extremely non-intuitive. Because what am I doing? I'm making the slit narrower and narrower and narrower and narrower. And what do you see ultimately? That the beam horizontally becomes wider and wider and wider and wider and wider and wider and wider. Now that is very non-intuitive, but it's the way the world works.
According to the quantum theory, even the most bizarre events have a probability of taking place. There's a certain probability that I will dissolve and simply rematerialize on the other side of that brick wall. Now, you may say to yourself, well, that's impossible. We've never seen anyone dissolve and rematerialize on the other side of brick walls. But we actually give this problem to our graduate students, to our PhD candidates. We ask them to calculate, using the quantum theory, what is the probability that you will find yourself on the other side of a brick wall? Now, to tell you the truth, you would have to wait longer than the lifetime of the universe for such an event to take place. So you don't have to worry. Your atoms are not going to dissolve, and you're not going to rematerialize on the other side of brick walls. But there is a probability you can calculate for that event happening.
And then you can ask yourself the question, do I understand it? I don't even know what that means, understanding. I have problems with that. Physics describes things, describes phenomena. And as long as it is predictable, as long as that formalism applied in a certain situation gives you the right answer, who cares? Who cares what the meaning is of understanding? I think I leave that up to philosophers. And I think they don't have a clue either, of course, but they